Picture a universe so young, so turbulent, that the very fabric of space and time was still stretching into existence. In those first fleeting moments after the Big Bang, before stars flickered to life, before galaxies spiraled into being, something extraordinary may have taken shape. Objects so dense, so powerful, they defy our understanding of physics itself. These are primordial black holes, ancient relics born not from collapsing stars, but from the raw energy of creation. Imagine remnants of the universe's infancy, lurking in the cosmic shadows for billions of years, hiding secrets that could rewrite everything we know about dark matter, gravity, and the fate of the cosmos. What if I told you these enigmatic objects might be all around us, invisible yet shaping the very structure of reality? Some could be as small as an atom, others as massive as 1,000 suns. They might be the missing piece to puzzles we've struggled to solve for decades, like the true nature of dark matter or the origins of supermassive black holes that anchor galaxies today. Or perhaps there's something even stranger, doorways to other dimensions or echoes of a multiverse we can't yet comprehend. The possibilities are as vast as the cosmos itself, and today we're diving deep into 30 of the most mind-bending theories about these cosmic ghosts. From the edges of theoretical physics to the cutting edge of astronomical observation, scientists are piecing together clues that could unlock the mysteries of primordial black holes. Some theories suggest they could explain bizarre gravitational waves we've detected, while others propose they're responsible for ancient cosmic anomalies that have baffled researchers for generations. Could they even be the key to understanding why our universe looks the way it does? Buckle up, because we're about to embark on a journey through time, space, and the very limits of human imagination, where every twist and turn reveals something more astonishing than the last. The story of primordial black holes isn't just about science. It's about our unending quest to uncover the universe's deepest, darkest secrets. And trust me, you won't want to miss a single moment of what comes next. One of the most tantalizing theories about primordial black holes suggests they could be the invisible architects of the cosmos, the very dark matter holding galaxies together. Right now, across the universe, stars orbit galactic centers at speeds that defy the laws of gravity as we understand them. According to our calculations, galaxies should be tearing themselves apart, yet something unseen exerts enough gravitational pull to keep them intact. Enter primordial black holes, not the kind formed from dying stars, but ones forged in the chaos of the universe's first seconds. Think of them as cosmic leftovers, condensed from regions of ultra-dense matter when the universe was a seething ocean of energy. Unlike black holes born from stellar collapse, these ancient objects could range wildly in size, from a speck smaller than an atom to something rivaling a mountain in mass. If enough of them exist, their collective gravity might perfectly explain the mysterious tug we attribute to dark matter. Picture a swarm of these invisible relics drifting through space, their presence felt only by the way they bend light and warp the motion of stars just like dark matter does. But proving this theory isn't simple. Primordial black holes don't emit light or radiation like stars, and the smallest ones could have evaporated by now due to Hawking radiation. So how do we hunt them? Astronomers look for subtle clues like brief flashes when a black hole's gravity magnifies light from a distant star, an effect called microlensing. Others search for ripples in space-time, the echoes of collisions between these ancient objects. The challenge, distinguishing primordial black holes from other cosmic phenomena, is like finding a single specific grain of sand on an endless beach. Yet the stakes couldn't be higher. If primordial black holes really are dark matter, it would solve one of physics' greatest puzzles while opening doors to even wilder possibilities. Maybe they helped seed the first galaxies, or perhaps they're the reason supermassive black holes appeared so early in cosmic history. Every observation, every experiment brings us closer to answers, or deeper into the mystery. One thing's certain, if this theory holds, the universe just got a lot stranger and a lot more fascinating. To understand how primordial black holes might have formed during the universe's earliest moments, we need to rewind to an era of unimaginable energy, cosmic inflation. In the tiniest fraction of a second after the Big Bang, the universe didn't just expand. It exploded outward at a rate so rapid, it makes today's accelerating expansion seem sluggish. This was inflation, a period when space itself stretched faster than light, smoothing out the cosmos and planting the seeds for everything we see today. But inflation wasn't perfectly uniform. Tiny quantum fluctuations, random ripples in the fabric of space-time, were stretched to enormous scales, creating pockets where matter was denser than others. Now, here's where things get fascinating. Some of these over-dense regions could have collapsed under their own gravity so violently, they bypassed the need for stars or galaxies entirely, snapping directly into black holes. Unlike the black holes we observe today, born from stellar collapse, these would have emerged from pure energy, like cosmic shortcuts in the universe's evolution. The key ingredient, inflation, had to end abruptly in certain areas, creating sharp density spikes. Picture a pot of water boiling furiously. Most bubbles pop harmlessly, but a few might merge into something far larger and more unstable. In the primordial universe, those bubbles of extreme density could have birthed black holes in an instant. This theory doesn't just offer a way to make primordial black holes, it ties them directly to one of cosmology's cornerstone ideas. Inflation explains why the universe looks so uniform on large scales, but those quantum fluctuations also gave rise to galaxies and galaxy clusters. If some of those fluctuations birthed black holes instead, it would mean these objects aren't just cosmic oddities, they're fossils from the same process that shaped the entire cosmos. But there's a catch. For this mechanism to work, inflation had to behave in very specific ways. The energy fields driving it would have needed sudden, localized drops in pressure, like cosmic potholes in the inflationary highway. Some models even suggest these black holes would form with a distinctive mass range, clustering in ways that could leave detectable imprints on the cosmic microwave background or the distribution of galaxies. What's truly mind-bending is the scale of this idea. If correct, primordial black holes could be direct evidence of inflation itself, a snapshot of quantum mechanics writ large across the universe. They'd be more than just mysterious dark matter candidates. They'd be time capsules from the first moments of reality. And that's what makes this theory so compelling. It doesn't just solve one puzzle. It weaves primordial black holes into the very foundation of how we understand the universe's birth. At the heart of nearly every galaxy lies a monstrous gravitational anchor, a supermassive black hole millions or even billions of times heavier than our Sun. But here's the puzzle. These behemoths appeared shockingly early in cosmic history, some fully formed when the universe was less than 1 billion years old. How did they grow so massive, so fast? One radical idea flips the script entirely. What if they didn't start big, but instead grew from tiny seeds scattered across the infant cosmos? Primordial black holes could be those seeds, lurking in the darkness long before the first stars ignited. Imagine a universe just a few 100 million years old, still dim and patchy with newborn galaxies. In this sparse landscape, a primordial black hole, perhaps only a few dozen times the mass of our Sun, drifts into a dense cloud of gas. Gravity takes over. The black hole begins feasting, pulling in material faster than it can radiate energy away. As matter spirals inward, friction heats it to unimaginable temperatures, creating a blazing disk of plasma. This isn't just growth, it's a runaway explosion of appetite where the black hole could double its size in mere millions of years. Scale this up across cosmic time, and you've got a recipe for the titans we see today. But the real smoking gun might lie in the most violent objects in the universe, quasars. These brilliant beacons, powered by supermassive black holes devouring entire stars worth of material every year, have been spotted at staggering distances, meaning we're seeing them as they were near the dawn of time. If primordial black holes seeded these monsters, their growth spurts would leave distinct fingerprints. Some quasars shine with a brightness that defies conventional models, as if their central black holes were already too large for their age. Could that mean they started with a head start, a primordial seed waiting to feast when the first galaxies coalesced? The math is compelling. Simulations show that even a modest-sized primordial black hole, placed in the right environment, could snowball into a supermassive giant given enough time and gas. But there's a twist: not all seeds would thrive. Some might starve in empty voids, while others merge in chaotic dances, creating even heavier anchors for future galaxies. This could explain why some supermassive black holes appear overweight for their cosmic era, while others seem to lag behind, yet mysteries remain. If primordial black holes seeded these giants, why don't we see more mid-sized black holes, the missing link between the tiny and the titanic? And how did they avoid getting kicked out of their host galaxies during violent mergers? The answers might lie in the way dark matter halos the invisible scaffolding of galaxies guided these seeds into place, nurturing them with steady streams of gas. Every new observation of distant quasars, every refinement in our simulations, brings us closer to knowing whether these ancient relics truly built the cosmic giants we marvel at today. One thing's certain: if this theory holds, the story of supermassive black holes isn't just about death and collapse. It's about rebirth and the quiet dominance of objects born from the universe's very first breath. Stephen Hawking's revolutionary insight turned our understanding of black holes on its head. What if these cosmic vacuum cleaners weren't entirely black after all? In the 1970s, he proposed something startling. Black holes could actually leak energy, slowly evaporating over time. This phenomenon, now called Hawking radiation, arises from quantum mechanics' bizarre rules near a black hole's event horizon. Virtual particles, fleeting pairs of matter and antimatter that usually annihilate each other instantly, can be torn apart by the black hole's immense gravity. If one particle falls in while the other escapes, the black hole effectively loses mass, radiating energy away like a dying ember. Now apply this to primordial black holes. While stellar mass black holes are so large they'd take longer than the current age of the universe to evaporate, smaller ones could vanish in a cosmic blink. A primordial black hole with the mass of a small asteroid might only last a few billion years, ending its life not with a whimper, but with a spectacular gamma-ray burst equivalent to 1 million nuclear bombs detonating at once. This raises a tantalizing possibility. What if we're witnessing the death throes of these ancient objects right now? Astronomers have scoured the skies for telltale flashes that could signal a primordial black hole's final moments. These bursts would be brief but intense, packing all the hole's remaining energy into a fiery farewell. Some researchers even suggest that certain unexplained gamma-ray events, like those detected by telescopes like Fermi or Swift, might be the last size of evaporating primordial black holes. The challenge: distinguishing these bursts from more mundane cosmic explosions, like neutron star collisions or supernova, is like picking out a single firefly's glow in a fireworks display. But the implications go far beyond detection. If Hawking radiation is real and primordial black holes are evaporating, it would mean these objects aren't just relics. They're ticking clocks, counting down to explosive finales that could illuminate the quantum nature of gravity itself. Some theories even suggest the smallest black holes might leave behind exotic remnants, strange particles, or even wormholes, doorways to other dimensions hidden in the fabric of space-time. Yet there's a cosmic irony here. The same radiation that could help us find primordial black holes might also explain why they're so elusive. If most of the lighter ones have already evaporated, what we're searching for could be the few survivors, the rare heavyweights that outlasted the universe's relentless march toward entropy. This dance between creation and destruction, between hidden relics and fiery ends, makes primordial black holes not just fossils of the early universe, but active participants in its ongoing story. And if we're lucky, the next flash in the night sky might just be one of them, whispering secrets from the dawn of time. The early universe wasn't the smooth, uniform expanse we might picture. It was a seething cauldron of density variations, subtle ripples in space-time that would one day sculpt everything from galaxies to galaxy clusters. But what if some of those ripples were extreme enough to collapse into primordial black holes? This idea hinges on a critical balance, regions where matter was packed so tightly, gravity overpowered the universe's rapid expansion, causing instant collapse. Think of it like a cosmic lottery, where the densest patches won the grim prize of becoming black holes while the rest stretched into the vast cosmic web we see today. These density variations aren't just theoretical, they're etched into the oldest light we can observe, the cosmic microwave background. The CMB is a snapshot of the universe at 380,000 years old, revealing faint temperature fluctuations that correspond to those early density differences. Most of these fluctuations are tiny, just 1 part in 100,000, but some regions might have been far more extreme. If certain areas were hundreds or even thousands of times denser than average, they could have crossed the threshold for black hole formation long before stars or galaxies existed. Here's where things get even more intriguing. Some anomalies in the CMB defy standard cosmological models, unusually cold spots, strange alignments, or unexpected voids. Could these be the fingerprints of primordial black holes? One theory suggests that a cluster of PBHs in the early universe would warp spacetime so severely they'd leave imprints in the CMB's temperature patterns. It's like finding footprints in cosmic concrete, evidence of something massive passing through when the universe was still setting, but the influence wouldn't stop there. Primordial black holes could also explain quirks in the large-scale structure of the cosmos. Simulations show that if PBHs existed in significant numbers, their gravity would act like invisible scaffolding, pulling matter into filaments and clusters earlier than expected. This might account for why some supermassive black holes and galaxies formed astonishingly fast, or why certain regions of space seem emptier than our models predict. Yet the puzzle isn't solved. If PBHs were born from these density spikes, why don't we see more evidence of them in the CMB's finer details? Some physicists argue that the smallest black holes would have evaporated by now, while others propose that their signatures are hidden in the noise of cosmic data, waiting for more sensitive telescopes to reveal them. The next generation of observatories, like the Euclid Space Telescope or the Square Kilometre Array, could finally spot these ghostly traces, turning anomalies into answers. What's breathtaking about this theory is how it ties the universe's largest structures to its smallest, most violent beginnings. Those primordial density variations didn't just shape galaxies. They might have birthed invisible monsters that still haunt the cosmos today. And if we're right, the key to understanding dark matter, supermassive black holes, and even the fate of the universe could lie in those faint, frozen ripples from the dawn of time. Gravitational waves, ripples in the fabric of spacetime itself, have revolutionized our understanding of the cosmos since their first detection in 2015. But what if some of these tremors aren't from the collisions of stars or black holes as we know them, but from something far older and more mysterious? Enter primordial black holes, potential cosmic specters whose mergers could be sending ghostly signals across the universe. When two PBHs spiral toward each other, locked in a gravitational dance billions of years in the making, their collision would unleash energy equivalent to millions of supernovae, all squeezed into a fraction of a second. The resulting gravitational waves would carry fingerprints of their origins, clues that might reveal whether we're hearing the echoes of the universe's first moments. The LIGO and Virgo observatories have already caught dozens of these spacetime ripples, most attributed to mergers of stellar mass black holes, but a handful of events defy expectations. Take GW190521, a detection in 2019 where two black holes merged, forming an object with a mass roughly 142 times that of our Sun. This falls squarely into the mass gap, a range where conventional astrophysics struggles to explain how such black holes could form from dying stars. Could this be a smoking gun for primordial black holes? Unlike stellar remnants, PBHs could form at almost any mass, neatly filling this gap and others like it. What makes this theory so compelling is the unique signature a PBH merger would leave. Stellar black holes typically form in pairs from binary star systems, meaning their spins and orbits follow predictable patterns. Primordial black holes, though, would pair up through random gravitational encounters over eons, leading to mergers with distinctive spin misalignments or wildly uneven masses. Some LIGO detections already show these oddball traits, like GW190814, where one black hole was nearly 9 times heavier than its partner, a mismatch far rarer in stellar evolution models. But the real game-changer would be spotting PBH mergers from the cosmic dawn. Current gravitational wave detectors aren't sensitive enough to catch collisions from the universe's first billion years, but next-generation instruments like the Einstein telescope or space-based LISA could listen for these ancient whispers. If PBHs were abundant enough, their early mergers might have forged a background hum of gravitational waves, a faint static permeating the cosmos. Detecting this would be like tuning into a radio station from the universe's infancy, broadcasting the violence of its earliest chapters. Yet the puzzle isn't just about individual events. If PBHs make up even a fraction of dark matter, their merger rate would depend on how they're distributed. Dense clusters of primordial black holes lurking in galactic halos or floating in intergalactic voids could produce bursts of mergers at specific frequencies. Some researchers propose that PBHs might explain why LIGO sees more heavy black hole mergers than predicted, a cosmic overabundance of primordial heavyweights colliding in the dark. The stakes here are monumental. Confirming PBH mergers wouldn't just solve the riddle of odd gravitational wave signals, it would rewrite the story of how structure formed in the universe. These ancient black holes could have been the seeds for the first stars, the anchors for proto-galaxies, or even the architects of the cosmic web itself. Every new chirp from LIGO brings us closer to knowing whether we're hearing the last gasps of dying stars or the echoes of creation's first monsters. And with each detection, the line between science fiction and reality blurs just a little more. For decades, astronomers have faced a cosmic accounting problem: where is all the ordinary matter? When we tally up the stars, gas, and dust we can observe, it adds up to only about half of the baryonic matter predicted by the Big Bang. This missing matter isn't exotic dark energy or mysterious particles. It's the protons and neutrons that should be out there, hidden in plain sight. One radical solution suggests primordial black holes might be the universe's ultimate vaults, locking away this missing baryonic matter in their inescapable grips. The story starts with Big Bang nucleosynthesis, that brief window seconds after creation when the universe was hot enough to fuse protons and neutrons into the first light elements. The amounts of hydrogen, helium, and lithium produced during this epoch depend critically on how much baryonic matter was present. Observations of these primordial elements match stunningly well with theoretical predictions, but only if we account for all baryons. Fast forward billions of years and our cosmic inventories come up short. So where did the rest go? Primordial black holes offer an elegant, if startling, answer. If PBHs formed in the early universe from ultra-dense pockets of baryonic matter, they could have swallowed enormous quantities of ordinary mass before stars even ignited. Picture a cosmic vacuum cleaner operating in reverse instead of sucking up dust. It hoards the very building blocks of reality. These black holes wouldn't need to be massive to solve the problem. A swarm of Earth-sized PBHs, each containing the mass of a small mountain, could collectively account for the missing matter without disrupting the delicate balance of nucleosynthesis. But there's a catch. If PBHs are the culprits, they'd need to avoid leaving obvious traces. Cosmic rays' high-energy particles zipping through space provide one critical test. When matter falls into black holes, it doesn't just vanish quietly. Friction and magnetic fields can accelerate particles to nearly light speed, creating detectable cosmic ray signatures. If too many baryons were locked in PBHs, we'd expect to see more of these high-energy particles than we actually observe. Yet some models suggest PBHs could swallow matter cleanly, especially if they're small enough to avoid tearing nearby gas into luminous accretion disks. The plot thickens when we consider the universe's most barren regions, the vast cosmic voids between galaxy clusters. These emptinesses aren't truly empty. They contain diffuse gas so thin it's nearly invisible. But even this sparse material falls short of explaining the missing baryons. Intriguingly, simulations show that primordial black holes could explain the discrepancy by gravitationally dragging baryons into these voids over cosmic time, redistributing matter without emitting the telltale radiation that would betray their presence. What makes this theory so compelling is its sheer audacity. Instead of hunting for faint gas clouds or elusive particles, we might be surrounded by invisible black holes that formed before the first stars. They wouldn't just solve the missing baryon puzzle, they'd rewrite the story of how structure emerged in the universe. Every galaxy, every star, every planet could exist in the gravitational shadow of these ancient relics, their presence felt only in the quiet absence of the matter they consumed. The next generation of X-ray telescopes and gravitational wave detectors might finally close this cosmic ledger, revealing whether the missing matter was lost or just hiding in the darkest corners of space-time. In the bizarre landscape of the early universe, reality may have been threaded with cosmic strings infinitely thin, unimaginably dense filaments of pure energy left over from the moment of creation. These aren't your everyday strings. Think of them as cracks frozen in the fabric of spacetime itself, relics of a phase transition when the fundamental forces of nature split apart. Like flaws in a cooling crystal, cosmic strings could have stretched across the cosmos, vibrating with enough gravitational fury to warp space around them. And if one of these strings ever collapsed or knotted upon itself, the resulting energy density might have been so extreme, it could have birthed a primordial black hole in an instant. The math behind this is mind-bending. Cosmic strings, if they exist, would be under immense tension, so much so that just a single kilometer of string could weigh as much as an entire planet. When such a string loops or intersects, the gravitational energy concentrated at that point could exceed the threshold needed for black hole formation. Unlike black holes born from matter collapsing under gravity, these would emerge from pure spacetime curvature, like knots pulled so tight they puncture reality itself. The resulting PBHs would carry a unique signature. Their masses would be tied directly to the string's tension, potentially creating a distinct population of black holes all within a narrow size range. But how would we ever spot such an exotic origin? One clue lies in their distribution. Cosmic strings wouldn't tangle randomly. They'd follow patterns set by the universe's earliest symmetry breaks. If PBHs formed from them, they might cluster in ways that defy conventional astrophysical models, perhaps lining up along invisible, ancient fault lines in space. Gravitational wave observatories could be key here. When cosmic strings vibrate or snap, they'd send out bursts of high-frequency spacetime ripples unlike anything from colliding stars or black holes. Future detectors like LISA or the Einstein telescope might catch these whispers, revealing whether the universe's darkest objects were spun from threads of pure geometry. There's even a wilder possibility. Some cosmic strings might still be out there today, lurking in the voids between galaxies. If so, their gravitational lensing effects could warp the light of distant quasars or stretch the images of far-off supernova in telltale ways. Astronomers have searched for these distortions, but so far no definitive cosmic string has been found. Yet the hunt continues, because if even one were discovered, it would rewrite our understanding of the universe's infancy and open the door to a whole new class of primordial black holes. What makes this theory so compelling is how it ties together two of cosmology's most elusive puzzles. Cosmic strings are predicted by many grand unified theories, while PBHs could solve mysteries from dark matter to galaxy formation. If the two are linked, it would mean the universe's structure, from the largest scales down to its darkest, densest objects, was shaped by defects in the very fabric of reality. Every gravitational wave detection, every anomalous lensing event, brings us closer to knowing whether these cosmic threads are real or just a beautiful figment of theoretical imagination. And if they're real, then the cosmos is far stranger and far more intricate than we ever dared dream. At the very edge of theoretical physics lies a realm where gravity and quantum mechanics collide, the Planck scale. This is the smallest possible length in the universe, a mind bending 10 to the power of negative 35 meters, where space-time itself becomes a seething quantum foam. If primordial black holes formed with masses near this scale, just a tiny fraction of a gram, they wouldn't just be cosmic oddities. They'd be portals to a new frontier of physics, objects so small and dense that they force us to confront the deepest questions about the nature of reality. Picture a black hole with the mass of a single dust mote, yet compressed into a space trillions of times smaller than an atom. At this scale, the very concept of a black hole blurs. Hawking radiation, which causes larger PBHs to evaporate over eons, would rage like a hurricane for these micro-relics, potentially vaporizing them in nanoseconds. But some theories suggest quantum gravitational effects, phenomena we don't yet fully understand, might stabilize them. Imagine space-time itself twisting into knots at these energies, creating structures so bizarre they defy conventional physics. These could be more than just black holes. They might be frozen fragments of the universe's first moments, preserving conditions we can't recreate in any lab. The implications are staggering. If Planck-scale PBHs exist today, they'd effectively be elementary particles with gravity, objects so small they'd zip through matter like ghosts, interacting only weakly with the world around them. Some models even propose they could be candidates for ultra-light dark matter, drifting through galaxies in vast, invisible clouds. Others speculate they might form exotic quantum states, behaving less like classical black holes and more like fuzzy, probabilistic blurs where the very idea of an event horizon breaks down. Detecting these relics would demand revolutionary technology. Traditional telescopes are useless here, but quantum gravity experiments or ultra-sensitive gravitational wave detectors tuned to high frequencies might one day catch their whispers. Some researchers propose looking for their evaporation signals, brief bursts of energy as they dissolve into the quantum vacuum. Others suggest their collective gravity could subtly alter the orbits of stars or bend light in unexpected ways. But the real prize isn't just finding them, it's what they'd teach us. Planck-scale PBHs would be living experiments in quantum gravity, offering clues to unite Einstein's relativity with the bizarre rules of the quantum world. They might reveal hidden dimensions, test string theory, or even hint at the existence of a multiverse. Every unanswered question about their survival, their behavior, and their role in the cosmos pushes the boundaries of what we know. And if we're lucky, the universe might still hold these tiny, ancient secrets waiting to be uncovered in the quantum noise of empty space. Black holes have long haunted physicists with a paradox so deep, it challenges the very foundations of quantum mechanics, the information paradox. At its core, this puzzle asks a seemingly simple question. When a black hole evaporates via Hawking radiation, what happens to all the information about the matter it once consumed? According to quantum theory, information can never be truly destroyed, yet black holes appear to erase it completely, violating one of science's most sacred principles. Primordial black holes, especially the tiniest ones nearing the end of their lifespans, might hold the key to unraveling this enigma. Think of a black hole as the universe's ultimate shredder. Toss in a book, and conventional physics says the information printed on its pages is lost forever, scrambled beyond recovery by the chaotic swirl beyond the event horizon. But quantum mechanics insists that information is indelible. It might be transformed but never erased. This clash isn't just academic. It hints at a gaping hole in our understanding of how gravity and quantum mechanics intertwine. Now imagine a primordial black hole, one so small it's been evaporating since the earliest epochs of the cosmos. As it nears its final moments, radiating away its last traces of energy, does it release trapped information back into the universe like a cosmic message in a bottle? Hawking's original calculations suggested the radiation emitted by black holes was purely thermal random noise carrying no meaningful data about what fell in. But later theories, like the holographic principle, proposed that information might be encoded on the black hole's surface, imprinted like a hologram on its event horizon. When applied to evaporating primordial black holes, this could mean their death throes aren't just random bursts of energy, but carefully structured releases of long-trapped quantum data. Picture a dying PBH as a locked vault finally cracking open, its contents once thought lost spilling back into the universe in subtle, quantum mechanical whispers. The stakes couldn't be higher. If primordial black holes preserve and eventually return information, it would validate quantum mechanics in the most extreme environment imaginable. Some models even suggest that the radiation emitted during a PBH's final seconds could contain faint but decodable echoes of its ancient meals, like cosmic background static hiding fragments of a billion-year-old broadcast. Detecting these signals would require instruments of unprecedented sensitivity, but the payoff would revolutionize physics. We're not just talking about solving a paradox, we're talking about glimpsing the universe's underlying code, written in the language of evaporating black holes. Yet mysteries remain. If information escapes, how does it avoid being scrambled beyond recognition? One bold idea posits that PBHs might form quantum hair, microscopic structures on their surfaces that retain data like cosmic barcodes. Others argue that the information isn't carried by the radiation at all, but instead encoded in the way the black hole's evaporation alters the fabric of space-time around it. The truth might lie somewhere between, in a realm where gravity and quantum mechanics merge into a theory we've yet to fully grasp. What makes primordial black holes such compelling test cases is their simplicity. Unlike their stellar mass cousins, which are cluttered with the debris of collapsed stars, PBHs formed from pure, dense energy in the early universe. Their evaporation is a clean experiment free from astrophysical noise. If we could catch one in its death throes, we might witness information's escape firsthand, a Rosetta Stone for decoding quantum gravity. Every unexplained gamma-ray flash, every anomalous particle burst could be a breadcrumb leading us closer to the answer. And in that answer, we might finally understand how the universe remembers, even when its darkest corners seem to forget. Imagine the early universe not as a smooth, uniform soup, but as a cosmic cauldron filled with bubbles, each one a pocket of reality where the fundamental forces behaved radically differently. These bubbles emerged during first-order phase transitions, moments when the infant universe shifted states like water freezing into ice, but on a scale that defies comprehension. During these transitions, regions of false vacuum, a metastable high-energy state, suddenly decayed into true vacuum, releasing staggering amounts of energy in violent bursts. And it's within this cosmic froth that primordial black holes could have formed, not from collapsing stars or dense matter, but from the explosive death throes of these false vacuum bubbles. The physics here is as beautiful as it is bizarre. Picture a universe where the Higgs field, the same field that gives particles mass, hadn't yet settled into its modern, stable state. Some regions might have been trapped in a false vacuum, like a ball balanced precariously on a hill, waiting to roll into a valley of lower energy. When one of these regions finally decayed, the energy released would have surged outward in a spherical wall, a shockwave of spacetime itself. If two such bubbles collided, or if a single bubble collapsed under its own curvature, the energy density at the intersection could have been so extreme that it pinched off into a black hole. These wouldn't be the gentle formations we see today. They'd be black holes born from raw symmetry breaking, cosmic scars left by the universe choosing its fundamental laws. What makes this theory so compelling is how tightly it ties primordial black holes to some of the most profound questions in particle physics. The masses of these PBHs wouldn't be random. They'd be set by the energy scale of the phase transition itself. For example, if this occurred during electroweak symmetry breaking, when the electromagnetic and weak forces split apart, the resulting black holes could be as light as a microgram. But if it happened at grand unification energies, where the strong force merges with the electroweak, we're talking about black holes massive enough to seed galaxies. This isn't just about black holes, it's a potential window into physics at energies so high, we'll never recreate them in any particle collider. Evidence for this might be hiding in the gravitational wave background. Just as colliding bubbles in a boiling pot create ripples, colliding vacuum bubbles in the early universe would have sent out space-time tremors at specific frequencies. Future observatories like LISA or the Einstein telescope could detect these echoes, revealing not just whether PBHs formed this way, but the precise moment in cosmic history when the forces of nature fractured into the ones we know today. Some models even predict PBHs from phase transitions would cluster in distinct patterns, like cosmic breadcrumbs leading us back to the universe's first symmetry breaks. Yet the wildest implication might be what this says about the multiverse. If our universe underwent multiple phase transitions, each creating its own population of PBHs, could other bubble universes, each with different physical constants, have forged their own black holes in similar ways? The idea teases a dizzying possibility. Primordial black holes might not just be relics of our cosmic infancy, but markers of realities beyond our own, drifting like shadows at the edges of spacetime. And if we're listening closely enough, their gravitational whispers could tell us stories not just about where we came from, but about universes we'll never see. Fast radio bursts, those brilliant, milliseconds-long flashes of cosmic radio waves, have puzzled astronomers since their discovery in 2007. These bursts pack the energy of hundreds of millions of suns into fleeting signals, appearing randomly across the sky with no obvious source. But what if some of these enigmatic events aren't coming from distant galaxies or colliding stars, but from something far older and darker? Enter primordial black holes lurking in the voids between stars, potentially triggering these cosmic fireworks in ways we're only beginning to unravel. One provocative theory suggests that when a primordial black hole passes near or through a neutron star, the gravitational chaos could ignite an FRB. Picture this: a PBH, invisible and ancient, drifts too close to a city-sized neutron star itself, a dense remnant of a supernova. The black hole's gravity distorts the neutron star's magnetic field, twisting it like a rubber band until it snaps. This sudden release of pent-up energy could launch a jet of charged particles, accelerating them to near-light speeds and producing the telltale radio blast we detect as an FRB. Unlike models that rely solely on neutron star mergers or magnetar flares, this scenario doesn't require rare alignments or catastrophic collisions. A single primordial black hole, wandering the galaxy for billions of years, might set off multiple bursts as it interacts with different stars. The evidence isn't just speculative. Some FRBs repeat at irregular intervals, a pattern that's hard to explain with one-time events like collisions. A PBH orbiting or periodically perturbing a neutron star could account for these sporadic reappearances. Even more intriguing, certain bursts show bizarre frequency structures drifting sub-pulses or bands of energy that might reflect the complex dance between a neutron star's magnetosphere and an intruding black hole's gravitational wake. It's as if the radio signal carries fingerprints of an invisible intruder, warping space-time as it passes, but the plot thickens when we consider alternative explanations. Magnetous neutron stars with unimaginably strong magnetic fields remain the leading candidates for many FRBs. When these stars undergo starquakes, their crusts crack under magnetic strain, releasing energy in explosive waves. Similarly, collisions between neutron stars or white dwarfs could generate bursts through shocks or magnetic reconnection. The challenge: primordial black holes don't leave behind the afterglows or X-ray counterparts seen in some FRBs, making them a stealthier but harder to confirm culprit. What tips the scales toward PBHs in some cases? A handful of FRBs defy conventional models entirely. Take FRB 190520, a burst detected in 2019 with no obvious host galaxy, drifting through intergalactic space like a ghost. If this signal came from a primordial black hole interacting with a rogue neutron star, one ejected from its galaxy during some ancient cosmic upheaval, it would explain the lack of a visible home. Similarly, bursts with unusually high dispersion measures indicating they've traveled through more gas than expected might trace back to PBHs lurking in dense interstellar clouds, their gravity funneling extra material into the signal's path. The stakes here are astronomical. If even a fraction of FRBs stem from primordial black holes, it would mean these ancient objects aren't just passive relics, they're active players in the cosmos, sculpting energetic phenomena we're only beginning to catalog. Future telescopes like the Square Kilometre Array could settle the debate by pinpointing FRB locations with unprecedented precision, or catching the faint gravitational distortions that might betray a PBH's presence. Until then, the mystery remains. Our fast radio bursts the death cries of collapsing stars, the tremors of magnetic monsters, or the echoes of invisible giants brushing past the universe's most volatile objects. The answer might rewrite not just the story of FRBs, but the hidden role of black holes born in the dawn of time. Deep in the labyrinth of particle physics lies one of the most elusive hypothetical particles ever conceived, the axion. Originally proposed to solve a quantum puzzle involving the strong nuclear force, these ghostly particles have since emerged as leading candidates for dark matter. But here's where things get even more intriguing. If axions exist, their dance with primordial black holes could reveal secrets about both these cosmic mysteries in one fell swoop. Axions are bizarre creatures. Unlike ordinary matter, they'd interact with the universe almost exclusively through gravity and weak quantum effects, making them nearly invisible to conventional detectors. But in the presence of intense magnetic fields or extreme gravity, like that near a black hole, axions might transform into photons, creating faint but detectable signals. Now imagine a primordial black hole drifting through space, its immense gravity warping the quantum fields around it. If axions permeate the cosmos as dark matter, they'd cluster around PBHs like moths to a flame, their density spiking in these gravitational wells. As these axions brush against the black hole's event horizon, quantum effects could trigger their conversion into radio waves, a subtle but telltale emission that our telescopes might one day catch. This isn't just theoretical daydreaming. Experiments like ADMX and Haystack are already hunting for axions by tuning ultra-sensitive detectors to search for their predicted photon conversions. A primordial black hole passing through Earth's vicinity, or even sitting quietly in our galactic halo, could amplify this signal dramatically. The gravity well of even a small PBH would act like a cosmic lens, focusing axions into a tighter stream and increasing the chances of detectable conversions. It's like turning the volume knob on the universe's quietest radio station, making whispers audible at last, but the connection goes deeper. If axions are real, their interactions with PBHs could solve another puzzle: why we haven't found certain types of black holes where we expect them. Some models suggest axions orbiting PBHs would emit gravitational waves, subtly siphoning energy away and causing the black holes to spiral inward over cosmic time. This process could explain why the universe isn't overrun with intermediate mass PBHs. They've been slowly evaporated or merged away by their own axion halos. The most tantalizing possibility: axions and PBHs might be locked in a feedback loop that shapes the cosmos. As primordial black holes move through axion-rich dark matter, their gravitational wakes could create dense axion stars or streams, which in turn influence where new black holes form. This cosmic tango might even leave imprints in the large-scale structure of the universe, subtly altering how galaxies cluster in ways we're only beginning to model. What makes this pairing so compelling is how it turns two mysteries into mutual solutions. Axions need a gravitational partner to make them detectable. PBHs need a particle interaction to explain their scarcity. Together, they could unlock doors we didn't even know existed, revealing not just the nature of dark matter, but the hidden architecture of space-time itself. Every unexplained radio signal, every anomaly in gravitational wave data, could be a clue waiting to connect these cosmic dots. And if we're right, the universe just handed us a Rosetta Stone written in the language of quantum gravity and shadowed particles. String theory paints a picture of reality far stranger than our familiar four dimensions, a universe woven from tiny, vibrating strings humming through 10 or 11 dimensions, most curled up so small we'll never perceive them directly. But what if these hidden dimensions weren't just mathematical abstractions? What if they left their fingerprints on some of the universe's most enigmatic objects, primordial black holes? In this shadowy realm of theoretical physics, extra dimensions could have twisted the very rules of black hole formation, birthing PBHs with properties that defy everything we know about gravity in our four-dimensional world. Take the concept of brains short for membranes floating in a higher dimensional bulk. In some string theory models, our entire universe might be a three-dimensional brain adrift in a vast, unseen expanse. If this is true, the early cosmos could have been a battleground where gravity, leaking into extra dimensions, behaved wildly differently. Under these conditions, forming a black hole wouldn't require squeezing matter into a tiny four-dimensional point. Instead, gravity's stronger pull in higher dimensions might have made PBH formation shockingly easy, like poking holes in wet paper. The result: black holes with unusual masses, evaporation rates, or even shapes, some perhaps stretching across dimensions we can't see. The real mind-bender comes when we ask how these higher dimensional PBHs would age. In our four-dimensional universe, Hawking radiation causes black holes to shrink slowly over eons. But in models with extra dimensions, evaporation could accelerate dramatically as energy leaks into hidden realms. A PBH that should have lasted billions of years might vanish in a cosmic blink, leaving behind bursts of high-energy particles or gravitational waves with telltale signatures. Some theories even suggest these black holes could temporarily unfurl into higher dimensions as they evaporate, creating space-time ripples detectable by future observatories like LISA, like hearing a splash from a pond in a room you can't enter. Detecting these ghosts would demand rethinking our tools. Traditional searches for PBHs rely on their gravitational lensing effects or Hawking radiation in familiar energy ranges. But higher dimensional black holes might distort light in bizarre ways, leaving lensing patterns that look stretched or asymmetric. Others could emit particles unique to string theory, like Kaluza-Klein modes, vibrations of extra dimensions that might appear in particle colliders as unexpected spikes of energy. Even their mergers would differ. colliding PBHs in higher dimensions could produce gravitational waves with frequencies or harmonics beyond what conventional relativity predicts. The implications stretch beyond black holes. If extra dimensions helped forge primordial black holes, their existence could explain why we haven't found certain predicted particles or why gravity seems oddly weak compared to other forces. It might even hint that PBHs aren't just cosmic relics, they're living proof of dimensions lurking just beyond our perception. Every unexplained gravitational wave signal, every anomalous particle detection, could be a whisper from a reality far larger than we imagined. And if we're right, the universe's darkest objects might be the very keys to unlocking its deepest secrets, hidden not in space, but in the folds of dimensions we've yet to see. Primordial black holes might be more than just cosmic relics. They could be time capsules, carrying encoded information about the universe's earliest moments in ways no other object can. Think of them as frozen snapshots of a time before the first stars, locked away behind event horizons for billions of years. As these ancient objects evaporate or collide, they could release traces of the conditions that forged them, offering us a direct line to the universe's infancy. When a PBH evaporates through Hawking radiation, it doesn't just vanish quietly. The particles it emits carry subtle clues about its origins. For instance, the ratio of different particle types, photons, neutrinos, even exotic relics like gravitons, could reveal the temperature and density of the universe when the black hole formed. If PBHs emerged during cosmic inflation, their radiation might bear imprints of quantum fluctuations from that era, like cosmic hieroglyphs waiting to be decoded. Even the timing of their evaporation could be a clue. A burst of gamma rays from a dying PBH today might signal it formed during an early phase transition, when the fundamental forces of nature were still splitting apart. But the real treasure might lie in their mergers. When two primordial black holes spiral together, the gravitational waves they produce ripple through space-time with a signature shaped by their formation. Unlike black holes born from stars, PBHs wouldn't be contaminated by heavier elements or stellar debris. Their clean, unaltered masses and spins could preserve a pristine record of the universe's density variations in its first seconds. Future detectors might even spot a population of PBHs, all with similar masses, a cosmic barcode pointing to a specific moment in cosmic history, like an assembly line of black holes stamped from the same primordial conditions. What's even more tantalizing is the possibility that PBHs could trap and preserve relics from beyond the standard model. Theories like supersymmetry or grand unification predict particles that vanished as the universe cooled. If these particles fell into primordial black holes early on, their signatures might re-emerge during evaporation, like messages in a bottle finally uncorked. Imagine detecting a shower of particles that haven't existed since the universe was a trillionth of a second old, a direct window into physics at energies no collider will ever reach. The challenge, of course, is learning to read these cosmic records, distinguishing PBH evaporation signals from mundane astrophysical events requires precision instruments and clever analysis. But the payoff would rewrite textbooks. We could test theories of inflation, measure the universe's expansion rate in its infancy, or even uncover evidence of sibling universes in the multiverse. Every unexplained particle burst, every odd gravitational wave chirp, could be a fragment of a story written at the dawn of time, and if we're listening closely enough, these ancient black holes might just tell it. One of the most perplexing mysteries in physics isn't found in the vastness of space, it's buried in the equations of particle theory. The hierarchy problem asks a deceptively simple question: why is gravity so unimaginably weaker than the other fundamental forces? Electromagnetism can yank a paperclip upward against Earth's entire gravitational pull, and the strong nuclear force binds atomic nuclei with a grip 100 times stronger still. Gravity, by comparison, is a featherweight. The difference is so staggering, it's like comparing a whisper to a supernova. But primordial black holes, those relics of the universe's first moments, might hold clues to this cosmic imbalance, not by their presence today, but by the conditions that forged them. Picture the infant universe, a seething cauldron where all forces were united. As the cosmos expanded and cooled, these forces split apart: first gravity, then the strong nuclear force, electromagnetism, and the weak force. But why did gravity break away so early, leaving it diluted compared to its siblings? Some theories suggest the answer lies in extra dimensions, realms beyond our perception where gravity's strength isn't feeble, it's just spread thin, like ink bleeding through layers of paper. If primordial black holes formed during this critical era, their properties could reflect these hidden dimensions. Smaller PBHs, evaporating quickly via Hawking radiation, might leak gravity into these unseen realms, explaining why we perceive it as weak in our four-dimensional slice of reality. But there's another twist. The hierarchy problem is deeply tied to the Higgs boson, the particle that gives others mass. The Higgs's mass is curiously light, a fact that seems to require absurdly fine-tuned cancellations in quantum calculations. One provocative idea posits that PBHs could have acted as cosmic stabilizers. If these black holes formed when the Higgs field was still settling into its current state, their gravity might have suppressed quantum fluctuations that would otherwise have driven the Higgs mass to extreme values. It's as if the universe used primordial black holes as counterweights, balancing the Higgs on a knife edge to create the conditions for atoms and life to exist. The smoking gun could lie in PBH mass distributions. If extra dimensions or Higgs field interactions shaped their formation, we'd expect specific, preferred masses, clusters of black holes all within a narrow range, like footprints in the snow pointing back to the moment gravity diverged from the other forces. Future gravitational wave observatories might spot these patterns in merging PBHs, while particle colliders could hunt for remnants of higher dimensional gravity in rare, high-energy collisions. Yet the boldest implication isn't just solving the hierarchy problem, it's realizing that the weakness of gravity might be an illusion. If primordial black holes thread through extra dimensions, their existence could mean gravity isn't feeble at all. We're just seeing the shadow of its true strength filtered through the folds of reality. Every unexplained gap in our theories, every anomaly in black hole behavior, might be a clue that gravity's quiet dominance is written in the language of dimensions we've yet to see, and the ancient black holes that remember when all forces were one. Magnetic fields thread through the cosmos today, guiding charged particles, shaping interstellar clouds, even influencing star formation. But in the universe's first moments, these fields might have been so unimaginably strong, they warped space-time itself into primordial black holes. Here's how it could happen. Picture the infant universe as a superheated plasma, a seething ocean of particles and energy. Turbulence in this plasma, combined with the universe's rapid expansion, could have amplified tiny magnetic seeds into colossal fields far stronger than anything we see now. Where these fields knotted and twisted, their energy might have concentrated enough to warp space so severely, it collapsed into black holes without needing any matter at all. This process hinges on magnetohydrodynamics, the interplay between magnetic fields and charged fluids. In the early universe's dense plasma, magnetic lines weren't just passive threads, they were dynamic, writhing entities that could transfer energy violently. When regions of ultra-strong fields became unstable, their energy could have funneled into tiny, spinning vortices. Under the right conditions, these vortices might have concentrated so much energy in such a small volume, they crossed the threshold for black hole formation. It's like twisting a rubber band until it snaps, except here, the snap creates a tear in space-time. The smoking gun for this theory could lie in the spins of primordial black holes. Magnetic fields don't just compress matter, they spin it. If PBHs formed this way, they'd likely inherit rapid rotations from their magnetic birth, potentially leaving detectable signatures in gravitational waves when they merge. Future observatories might spot these telltale spins, distinguishing PBHs forged by magnetism from those born through other mechanisms, but the universe doesn't make it easy. Today's magnetic fields are far weaker, diluted by billions of years of cosmic expansion. To test this idea, scientists look for indirect clues like the imprint of early magnetism on the cosmic microwave background, or anomalies in how galaxies align along magnetic lines. Some models even suggest these magnetic PBHs could have skewed the distribution of dark matter, creating faint but detectable patterns in the large-scale structure of the cosmos. Yet constraints exist. If magnetic fields were too strong, they'd have left glaring imprints on the CMB that we don't observe, too weak, and they couldn't have forged black holes at all. Walking this tightrope requires precise physics, a Goldilocks scenario where turbulence, field strength, and plasma density align just so. But if they did, the implications are staggering. Not only would this reveal a new path to black hole formation, but it would mean the universe's magnetic tapestry isn't just a backdrop. It's an active weaver, spinning darkness out of pure energy in the cosmic dawn. What if our universe isn't the only one where primordial black holes lurk in the cosmic shadows? The multiverse theory suggests reality might be a vast tapestry of parallel universes, each with its own laws of physics, constants, and history. In some of these realms, PBHs could be far more common or far rarer than in our own, sculpted by the unique conditions of their birth. Picture a universe where inflation lasted longer, stretching quantum fluctuations into even wilder density variations. There, primordial black holes might dominate entire galaxies, crowding space so densely they collide constantly. Or imagine a cosmos where the strong nuclear force was slightly weaker, preventing matter from clumping densely enough to form black holes at all. These alternate realities could be laboratories for extremes we'll never see here, where PBHs aren't just curiosities, they're the architects of their universe's fates. This raises a haunting question: why does our universe seem so finely tuned for life? The anthropic principle suggests we observe conditions suitable for our existence precisely because we couldn't exist otherwise. If PBHs were more abundant, their gravity might have disrupted galaxy formation, preventing stars and planets from ever taking shape. Too few, and the lack of early seeds for cosmic structure could have left the universe a featureless void. Our Goldilocks PBH abundance just enough to influence dark matter and galaxy formation, but not enough to sterilize the cosmos, might not be a cosmic accident. It could be a selection effect, a shadow of the multiverse's infinite variety where only rare universes like ours strike the delicate balance for complexity. Some theories take this further, proposing PBHs as literal bridges between universes. In brainworld scenarios where our universe floats like a sheet in a higher dimensional bulk, colliding brains could generate black holes that puncture space-time, linking separate realities. These PBHs wouldn't just be relics, they'd be scars from ancient cosmic collisions, possibly even carrying traces of other universes' physics in their evaporation signals. The mind reels at the thought: what if the gamma ray burst from a dying PBH carries imprints of dimensions where gravity is stronger, or where the speed of light is different? Yet the multiverse connection isn't purely speculative. If we discover PBHs with certain mass ranges or clustering patterns that defy conventional formation models, it could hint at physics beyond our universe's framework. For instance, a sharp cutoff in PBH masses, like finding none heavier than a certain threshold, might reflect limits imposed by higher dimensional gravity in a sibling universe. Similarly, anomalous gravitational wave backgrounds could carry echoes of PBH formation in neighboring brains, like hearing muffled thunder from a storm just beyond the horizon. The profound irony is that the darkest, most elusive objects in our cosmos might be the very keys to illuminating realities beyond our own. Whether as cosmic accidents, multiversal fingerprints, or anthropic necessities, primordial black holes could be more than just our universe's ancient ghosts. They might be messengers from a vast and hidden metacosmos, whispering secrets about why our reality looks the way it does and what other wonders lie beyond the veil. At the bleeding edge of theoretical physics lies an idea so strange it sounds like science fiction. What if evaporating primordial black holes aren't just cosmic relics, but nature's most powerful quantum computers? Picture this as a PBH nears the end of its life, radiating away particles via Hawking radiation. Its event horizon isn't just a one-way street into oblivion. According to some interpretations of quantum mechanics, information trapped inside could be encoded in the radiation itself, transforming the black hole's death throes into a complex calculation unfolding across spacetime. This isn't just random noise, it's a cosmic-scale quantum algorithm, processing information with every particle it emits. The foundation for this wild idea comes from the holographic principle, which suggests all the information inside a black hole is somehow stored on its two-dimensional surface, like a cosmic DVD. As the black hole shrinks, this information gets imprinted onto the Hawking radiation in subtle quantum correlations. In essence, the evaporation process could be performing a form of quantum error correction, untangling and recombining quantum states in ways that mirror the operations of a quantum computer. The difference, instead of qubits in a lab, the processor here is spacetime itself, warped by gravity into performing computations we can barely fathom. But how would we ever detect such a thing? One clue might lie in the radiation's fine details. If a PBH is performing quantum computations, its emitted particles wouldn't be entirely random. They'd carry faint but detectable patterns like cosmic Morse code hidden in static. Some theorists suggest these patterns could show up as anomalies in gamma-ray bursts, with certain energy distributions or timing quirks that defy conventional astrophysical explanations. It's the kind of signal that next-generation telescopes, like the Cherenkov Telescope Array, might spot if we know what to look for. The implications spiral even further when we consider scale. A stellar mass black hole computing for billions of years is one thing, but what about a micro-PBH evaporating in a flash? These tiny monsters could act like quantum fireworks, performing staggeringly complex operations in nanoseconds before vanishing. If enough of them existed in the early universe, their collective computations might have left imprints on the cosmic microwave background or the distribution of dark matter, like ghostly fingerprints from a universe that wasn't just evolving but calculating. Of course, not all physicists buy into this radical vision. Critics argue that without a clear mechanism to program these black holes, any computations would be as random as rolling dice. Others point out that even if PBHs are doing quantum math, decoding the output from Hawking radiation would be like trying to reconstruct a symphony from a handful of scattered notes. Yet the mere possibility forces us to ask profound questions. Could computation be a fundamental feature of reality, woven into the fabric of gravity and quantum mechanics? And if so, what might the universe have been calculating all this time? The beauty of this theory is how it blurs the line between physics and metaphysics. If evaporating PBHs are indeed quantum computers, then the cosmos isn't just a stage for particles and forces, it's an unimaginably vast processor, running equations we're only beginning to glimpse. Every unexplained burst of radiation, every odd correlation in particle data, might be a fragment of a cosmic program older than time itself. And if we're clever enough to crack the code, we might just discover that the universe hasn't just been expanding and cooling, it's been thinking. The Fermi paradox presents one of the universe's great enigmas. If life is statistically likely, why haven't we found any traces of extraterrestrial civilizations? Among the many proposed solutions, from self-destruction to cosmic isolation, one of the most unsettling involves primordial black holes. These ancient relics, sprinkled across galaxies since the dawn of time, might be silently shaping the fate of intelligent life in ways we're only beginning to grasp. Consider the hazards PBHs could pose on galactic scales. A wandering primordial black hole, even one just a few kilometers wide, wouldn't just drift harmlessly through space. Its gravity could shred planetary systems, flinging planets from their orbits or hurling comets into interstellar chaos. A single close pass might destabilize a star's Oort cloud, triggering bombardment events that reset the clock on biological evolution. Worse yet, PBHs could lurk undetected in the dark between stars, invisible until their gravitational influence twists the paths of spacecraft or alters the delicate balance needed for stable climates. If civilizations rise only to be snuffed out by these cosmic landmines, it might explain why the universe seems so quiet. But the danger isn't just physical. PBHs could warp the very conditions necessary for life's emergence. Recent simulations suggest that clusters of primordial black holes might skew the distribution of dark matter in galaxies, creating dead zones where excessive radiation or gravitational turbulence prevents complex chemistry from taking hold. Imagine entire spiral arms rendered sterile by the unseen pull of PBHs, their influence nudging star-forming regions just far enough apart to delay or disrupt the birth of life-friendly planets. Over billions of years, these subtle effects could funnel civilizations into rare, fleeting pockets of habitability, explaining both our solitude and our precarious position in cosmic history. The paradox deepens when we consider time. Primordial black holes formed in the universe's first seconds, meaning they've had eons to shape galactic ecosystems. Early civilizations might have faced far greater risks, with PBHs more abundant before evaporation or ejection from galaxies. If intelligent life tends to arise late in cosmic history, as Earth did, it could simply be because earlier attempts were quashed by a younger, more hostile universe teeming with these gravitational predators. Yet there's a provocative twist. PBHs might not just be agents of destruction, they could be silent shepherds. Some models suggest their gravity could accelerate panspermia, hurling life-bearing debris between star systems. Others propose that civilizations advanced enough to detect PBHs might use them as navigation beacons or energy sources, turning cosmic hazards into tools. The chilling counterpoint: any society reaching that level of mastery would have to survive the gauntlet first. A filter so severe it leaves the universe appearing empty. What makes this theory so haunting is its universality. Unlike asteroid impacts or supernova, PBHs don't fade with time. They persist, invisible and patient, their influence woven into the fabric of galactic evolution. If we're alone, it might not be by chance or choice, but because the cosmos itself is threaded with silent sentinels, standing guard over islands of life in an ocean of darkness. And if we ever do find others, their survival could reveal just how rare or resilient intelligence truly is in a universe where danger hides in the void itself. Supersymmetry, one of the most elegant ideas in modern physics, proposes that every known particle has a hidden, heavier twin waiting to be discovered. These sparticles could solve some of the universe's deepest mysteries, from the nature of dark matter to the unification of fundamental forces. But here's where it gets even more intriguing. If supersymmetry is real, these exotic particles might have played a starring role in birthing primordial black holes during the universe's fiery infancy. Picture the early cosmos, a seething plasma where energy densities were so extreme, matter and antimatter collided relentlessly. In this chaos, supersymmetric particles, like the photino or gravitino, could have formed in abundance, their unusual properties tipping the scales toward black hole formation. Unlike ordinary matter, sparticles wouldn't annihilate as efficiently with their counterparts. This asymmetry might have created dense pockets of residual particles, clumping together under gravity's pull until they crossed the threshold for collapse. Think of it like cosmic breadcrumbs left by supersymmetry, gathering into gravitational knots that became PBHs. The smoking gun for this theory could lie in the mass range of these black holes. Supersymmetry predicts specific energy scales like the electroweak scale, where the Higgs boson operates that would naturally produce PBHs within certain mass windows. If we discover a population of primordial black holes all clustered around, say, 100 trillion tons, it could mirror the expected mass of sparkle dark matter candidates. That's not just a coincidence, it's a potential fingerprint of supersymmetry etched into the cosmos itself. This isn't just theoretical speculation. Particle colliders like the Large Hadron Collider are actively hunting for sparkles, slamming protons together at near-light speeds to recreate conditions last seen a fraction of a second after the Big Bang. So far, no definitive sparkle has been found, but the search is far from over. Upgrades to the LHC and next-generation colliders, like the proposed Future Circular Collider, could push energy frontiers high enough to uncover these elusive twins. If they exist, their properties could refine our models of PBH formation, revealing whether supersymmetry truly sculpted the universe's dark archives. Yet the implications stretch beyond colliders. Supersymmetric PBHs would evaporate differently than their standard counterparts, their Hawking radiation possibly laced with exotic particles unique to SUSY. Observatories hunting for gamma-ray bursts or antimatter anomalies might stumble upon these signatures, linking microscopic particle physics to the universe's largest structures. It's a staggering thought that the key to understanding primordial black holes could lie not in distant galaxies, but in the quantum rubble of particle collisions beneath the Swiss-French border. What makes this theory so compelling is how it ties the infinitesimally small to the astronomically vast. Supersymmetry was conceived to solve quantum riddles, yet it might also hold the secret to black holes older than stars. Every null result in sparkle searches, every unexplained gravitational wave signal, brings us closer to knowing whether our universe is truly supersymmetric, and whether its hidden particles once conspired to weave darkness into the fabric of spacetime. One of the most radical ideas in modern physics suggests that reality as we know it might be a projection, a cosmic illusion where the three-dimensional universe we experience is actually encoded on a two-dimensional surface at its boundaries. This is the holographic principle, a framework where black holes play a starring role. Their event horizons, according to this theory, aren't just points of no return. They're vast hard drives storing every bit of information that falls inside. Now apply this to primordial black holes, relics forged in the universe's first moments. If the holographic principle holds, these ancient objects could be more than just gravitational traps. They might be the universe's original data storage devices, preserving quantum information from the dawn of time. The math behind this is both beautiful and mind-bending. In the holographic framework, a black hole's entropy, a measure of its information content, isn't proportional to its volume, but to the area of its event horizon. That means every PBH, no matter how small, carries a cosmic library on its surface, with each square Planck length unit acting like a pixel in a grand cosmic image. For primordial black holes, this has staggering implications. If they formed during inflation or phase transitions, their surfaces could have imprinted quantum fluctuations from those eras, preserving data about conditions we can't recreate in any lab. It's as if the universe left us a billion-year-old hard drive encrypted in spacetime itself. But here's where it gets even stranger. The holographic principle suggests that information isn't lost inside a black hole. It's scrambled and eventually radiated back out via Hawking radiation. For PBHs evaporating today, that means their death throes might not just be random bursts of particles, but carefully structured releases of encoded data. Imagine detecting a gamma-ray flash from a dying PBH and realizing it's not noise, it's a message from the early universe, a whisper of quantum fluctuations frozen during cosmic inflation. The challenge decoding that signal would require understanding quantum gravity at a level we haven't yet reached. This isn't just theoretical hand-waving. The holographic principle has passed rigorous tests like correctly predicting the entropy of certain black holes. If it applies to PBHs, it could solve one of cosmology's thorniest problems, the black hole information paradox, by showing how these objects preserve and eventually return quantum information. Some models even suggest that PBH mergers would create gravitational waves with subtle holographic imprints, patterns that next-generation detectors like the Einstein telescope might one day spot. The implications stretch to the nature of reality itself. If the holographic principle is true and PBHs are part of that cosmic code, then these ancient black holes aren't just objects in space, they're pixels in a far larger image, fragments of a universe that operates like a quantum computer. Every collision, every evaporation, every ripple in space-time could be part of a computation we're only beginning to understand. And that means the key to quantum gravity might not lie in a lab or a telescope, but in the holographic shadows of black holes born with the universe itself. Dark energy, the mysterious force accelerating the universe's expansion, remains one of cosmology's most perplexing puzzles. We know it's there, warping the cosmos on grand scales, but its true nature is hidden, its effects felt rather than seen. Now imagine if primordial black holes, those ancient relics drifting unseen through space, could act as cosmic breadcrumbs leading us to dark energy's doorstep. Here's how it might work. Dark energy doesn't just push galaxies apart, it subtly alters the fabric of spacetime itself, shaping how structures form over billions of years. Primordial black holes, especially those clustered in halos or voids, would respond to these changes in telltale ways. Their distribution across the universe wouldn't just reflect gravity's pull, it would encode the imprint of dark energy's push. Think of PBHs as buoys floating on an invisible ocean, their positions shifting with currents we can't directly observe. By mapping where these black holes congregate or avoid, we might reverse engineer the forces guiding them, isolating dark energy's fingerprint from the noise of cosmic expansion. The key lies in large-scale surveys, projects like the upcoming Euclid Space Telescope or the Vera-C, Rubin Observatory's legacy survey of space and time. These missions won't just catalog galaxies, they'll hunt for gravitational lensing distortions, subtle warps in starlight caused by unseen mass, including PBHs. If dark energy's repulsive force has stretched the cosmic web into an unusual configuration, primordial black holes should cluster differently than predicted by gravity alone. Their arrangement might reveal voids emptier than expected, or filaments stretched thinner, betraying dark energy's influence on the universe's scaffolding. One tantalizing clue could come from timing. Dark energy's dominance began around 5 billion years ago, a cosmological blink of an eye compared to PBH's 13 billion-year lifespan. If primordial black holes are indeed relics of the universe's infancy, their present-day distribution should carry scars from this transition, like fossils preserving the moment the cosmos shifted gears. Simulations suggest PBHs in regions where dark energy kicked in early would have been yanked apart faster, their clustering patterns diverging from those in slower evolving zones. Spotting this split could help us pinpoint whether dark energy's strength has changed over time, a critical test for theories suggesting it's not a constant force, but one that evolves. Yet the real breakthrough might come from anomalies. If PBHs are unevenly distributed in ways that defy conventional models, say, unexplained gaps in their expected abundance at certain distances, it could hint at dark energy interacting with itself or other forces in ways we've yet to imagine. Some speculative theories even propose that dark energy's repulsive nature might have selectively evaporated smaller PBHs in specific cosmic epochs, leaving behind a skewed population that mirrors its hidden properties. The beauty of this idea is its duality. Primordial black holes are both relics of the past and probes of the present, their paths through space-time etched with clues about the universe's darkest secrets. Every lensing event, every odd clustering pattern, could be a stitch in the tapestry of dark energy's true nature. And if we're right, these ancient objects born in the universe's first moments might finally illuminate the force that will dictate its ultimate fate. Neutrinos are the universe's most elusive particles, ghostly travelers that slip through entire planets like they're not even there. But rewind to the first seconds after the Big Bang, and these phantoms might have been the architects of some of the cosmos' darkest secrets. In the unimaginable heat of the infant universe, neutrinos weren't just abundant, they were crammed together at densities so extreme their sheer numbers could have warped spacetime itself into primordial black holes. Here's how it could have happened. In the early universe's quark-gluon plasma, neutrinos weren't the loners they are today. They were packed shoulder to shoulder, trillions of them per cubic centimeter, constantly colliding and interacting. Under normal circumstances, neutrinos barely notice each other. Their weak interactions make them terrible at clumping. But in those first moments, gravity wasn't the only force at play. Quantum effects could have amplified tiny density fluctuations, creating pockets where neutrinos clustered just tightly enough for their combined mass to tip the scales. Picture a cosmic game of bumper cars where, by sheer chance, one corner of the arena gets overcrowded. The weight of all those particles bends spacetime until, snap, it collapses into a black hole, forged not from stars or dark matter, but from a crush of neutrinos trapped in their own gravitational well. The smoking gun for this theory might lie in the cosmic neutrino background, the relic radiation left over from when neutrinos decoupled from matter just 1 second after the Big Bang. Unlike the cosmic microwave background, this neutrino echo is fiendishly hard to detect, but it carries imprints of early density variations. If PBHs formed from neutrino overdensities, their birthplaces should correspond to subtle hotspots in this background, like shadows of ancient traffic jams in the particle soup. Future observatories like Ptolemy or neutrino telescopes buried deep in Antarctic ice might one day spot these irregularities, revealing whether the universe's lightest particles birthed its heaviest objects. But there's a catch. Neutrinos move fast close to light speed in the early universe, and speedy particles resist gravitational collapse. For this mechanism to work, something would have needed to slow them down, if only briefly. Enter the neutrinos' rarely discussed secret. They might have a tiny bit of mass which could have made them sluggish enough in certain high-density regions to trigger collapse. Alternatively, interactions with hypothetical particles like sterile neutrinos or axions could have provided the necessary friction. If we discover evidence of such interactions, it wouldn't just explain PBH formation, it would crack open decades of neutrino physics, potentially solving why these particles have mass at all. The implications ripple outward. Neutrino-spawned PBHs would have a distinct mass range, heavier than those from quantum fluctuations, but lighter than those born from cosmic phase transitions. That sweet spot could explain why we've struggled to spot PBHs so far. They might be hiding in a mass range just beyond our current detection thresholds. Even more tantalizing, if neutrinos did forge black holes, their distribution could mirror the large-scale structure of the neutrino background itself, creating a cosmic web of PBHs woven from the universe's faintest particles. This idea blurs the line between particle physics and cosmology, suggesting that the answers to some of our biggest cosmic mysteries might be written in the language of the smallest, most elusive particles. Every neutrino detected in underground labs, every anomaly in the cosmic microwave background, could be a breadcrumb leading us back to a time when the universe was so dense, even ghosts could cast shadows dark enough to swallow light itself. Time flows forward like an unstoppable river, and we've grown so accustomed to its one-way march that we rarely question why. But what if the very direction of time, the arrow that separates past from future, could be shaped by the most enigmatic objects in the universe? Primordial black holes, those ancient relics from the dawn of creation, might hold a surprising connection to time's relentless forward push, all thanks to the delicate dance between gravity and entropy. At the heart of this mystery lies the second law of thermodynamics. the principle that disorder or entropy in a closed system always increases over time. It's why shattered glass doesn't spontaneously reassemble, and why heat flows from hot to cold, never the reverse. But black holes, especially those evaporating via Hawking radiation, play by unusual rules. When matter falls into a black hole, it vanishes from our universe's ledger, taking its entropy with it. For decades, physicists assumed this meant black holes were entropy destroyers until Stephen Hawking proved otherwise. His calculations revealed that black holes actually possess entropy proportional to their surface area, not their volume. And as they evaporate, they don't erase entropy, they release it back into the cosmos in a torrent of radiation. Now imagine countless primordial black holes peppered across the universe, each one a tiny entropy factory. As they emit Hawking radiation, they're not just fading into oblivion, they're actively shuffling the cosmic deck, injecting disorder into the universe at every moment. This constant drizzle of entropy from evaporating PBHs could act like a current beneath time's arrow, reinforcing its direction. In regions dense with these ancient objects, the local flow of time might even differ subtly from emptier voids, as the collective evaporation of PBHs tweaks the entropy gradient that defines past and future. But here's where it gets truly mind-bending. Some theories suggest that if enough primordial black holes evaporated in a short window, say, during a violent phase of the early universe, their combined entropy dump could have temporarily overwhelmed the arrow of time itself. Picture a cosmic traffic jam where the usual rules break down and for a fleeting instant cause and effect stutter. While this wouldn't mean time reversing, it might create pockets where the distinction between past and future blurs like eddies in a stream flowing against the current. The implications ripple even further when we consider quantum gravity. At the Planck scale, near the final moments of a PBH's evaporation, space-time itself may become frothy and uncertain. Under these extreme conditions, the very notion of linear time could dissolve, leaving behind a realm where entropy fluctuates wildly. If primordial black holes were numerous enough in the early cosmos, their deaths might have woven threads of temporal chaos into the fabric of the universe, threads that, once pulled, could reveal why time behaves as it does on large scales. What's astonishing is that this idea turns black holes from cosmic oddities into essential players in time's grand narrative. Without them, the universe's entropy budget might look radically different, potentially altering how the arrow of time emerged from the Big Bang's primordial soup. Every evaporating PBH, from the tiniest quantum speck to a mountain-sized relic, could be a ticking clock in the background of reality, quietly ensuring that the future stays well the future. And if we're right, the echoes of their influence might still linger in the subtle thermodynamics of the cosmos today. What if some primordial black holes aren't just cosmic dead ends but secret tunnels through space-time itself? The idea of wormholes, bridges connecting distant points in the universe, or even different universes entirely, has long been the stuff of science fiction. But buried in the equations of general relativity, there's a tantalizing possibility. Certain primordial black holes could be natural wormhole mouths forged in the chaos of the early cosmos. Picture spacetime as a sheet of paper crumpled by the violence of the Big Bang. In that turbulence, regions of extreme curvature might have pinched off into structures where space folds back on itself, creating shortcuts between points that should be light years apart. Unlike black holes formed from collapsing stars which trap matter forever, these wormhole-linked PBHs could theoretically let something pass through, if they're threaded with exotic matter, a hypothetical substance with negative energy that counters gravity's crushing grip. Without it, the wormhole would snap shut like a rubber band, severing the connection instantly. But if conditions were just right in the early universe, say, during a phase transition where quantum fields briefly flared with negative energy, primordial wormholes might have been frozen into existence before spacetime stabilized. Theoretical models suggest these wormhole-bearing PBHs would have unique signatures, For starters, their gravitational effects would differ subtly from ordinary black holes. A wormhole throat doesn't terminate in a singularity. It funnels into another region of space-time, meaning infalling matter wouldn't produce the same X-ray flares or accretion disks we associate with classic black holes. Instead, we might detect bizarre lensing patterns, light from distant stars bending around the PBH in ways that reveal a hollow center, or even duplicate images of the same object as light slips through the wormhole and back out. Testing this wild idea isn't impossible. Some physicists propose hunting for PBHs with anomalous spin rates. Wormholes connected to rotating black holes known as Kerr wormholes would impart a distinct wobble to nearby stars, a motion that telescopes like Gaia could potentially spot. Others suggest looking for gravitational wave echoes. Ripples from a PBH merger might bounce inside a wormhole throat, producing faint secondary signals milliseconds after the main event. These echoes, if found, would be smoking gun evidence that something stranger than a singularity lurks inside, but the boldest test might come from quantum entanglement. If wormholes are the geometric manifestation of quantum connections, a concept known as ER equals EPR, then entangled particles near a PBH could exhibit correlations that defy classical physics. Experiments aiming to probe the quantum behavior of black holes, like measuring Hawking radiation pairs, might accidentally stumble upon wormhole signatures hidden in the noise. Of course, not all physicists buy into this cosmic shortcut fantasy. Critics argue that stable wormholes require conditions so fine-tuned they're effectively impossible in nature. The exotic matter needed to prop them open has never been observed, and even if it exists, maintaining a traversable wormhole across billions of years seems ludicrously improbable. Then again, the universe has surprised us before. If primordial black holes really are wormhole gateways, it would mean the cosmos is laced with hidden passages, a labyrinth we've only begun to map. And somewhere in the static of gravitational waves or the flicker of distant starlight, the evidence might already be waiting. Among the most radical theories about primordial black holes is the idea that they aren't just relics of our universe's infancy. They could be cosmic shrapnel from collisions between entire other universes. This mind-bending concept emerges from the theory of eternal inflation, where our cosmos isn't a one-time event but one bubble in an endless, frothing sea of universes, each with its own physics and dimensions. In this chaotic multiverse, when two of these bubble universes brush against each other, the collision could unleash titanic energies, warping space-time so violently that it collapses into primordial black holes. These wouldn't be ordinary black holes, they'd be artifacts of a reality beyond our own, carrying imprints of laws and forces we can scarcely imagine. Imagine the scene: two universes, each expanding at breakneck speeds, their edges vast, seething walls of false vacuum energy slamming together. The impact wouldn't be like two soap bubbles merging gently. It would be a cataclysm, a space-time earthquake radiating gravitational shockwaves. At the epicenter, the energy density could spike so high that pockets of space-time pinch off, birthing black holes in an instant. These PBHs would be unique fossils, their masses and spins potentially reflecting the properties of their parent universes. Some might be freakishly dense, hinting at a cosmos where gravity was stronger. Others could evaporate anomalously fast, suggesting dimensions beyond our familiar four. The real smoking gun: these collisions wouldn't just leave behind black holes, they'd scar the cosmic microwave background. When bubble universes collide, they create asymmetric bruises. In the CMB's temperature patterns, regions slightly hotter or colder than their surroundings, shaped by the gravitational chaos of the impact. Planck satellite data has already flagged curious anomalies in the CMB, like the infamous cold spot, a vast, inexplicably chilly region in the sky. While other explanations exist, one tantalizing possibility is that we're seeing the aftermath of a multiversal fender bender, with primordial black holes lurking nearby like debris from the wreck. But how could we ever prove such a wild idea? The key might lie in gravitational wave astronomy. If PBHs from bubble collisions exist, they'd likely cluster in specific, non-random distributions, perhaps along great circles in the sky, tracing the shock front of an ancient collision. Future observatories like the space-based LIGO detector could spot mergers between these PBHs, revealing whether their orbital patterns match predictions from multiverse models. Even stranger, if some PBHs formed from universes with different fundamental constants, their mergers might produce gravitational waves with bizarre frequencies or polarizations, screaming, "I'm not from around here," in the language of space-time ripples. What's staggering about this theory isn't just its scale, it's the implication that primordial black holes could be messengers from realities where physics itself operates differently. A single PBH drifting through our galaxy might be the only tangible evidence of a cosmos where light travels faster or where time flows backward. And if we're bold enough to read the clues, these ancient black holes could rewrite not just our understanding of the universe, but of the multiverse itself. The next time you gaze at the night sky, consider this. Some of the darkness out there might not be empty space at all, but windows or scars from a collision with a universe we'll never see. What if the universe we see, touch, and study isn't the base layer of reality, but an incredibly advanced simulation? This provocative idea, known as the simulation hypothesis, suggests our entire cosmos could be an artificial construct running on some unfathomable computer. And if that's true, primordial black holes might not just be cosmic relics, they could be glitches in the code, artifacts left behind by the programmers, or even deliberate markers hidden in the fabric of the simulation itself. Think of it like this: in a simulated universe, every particle, every force, every law of physics would ultimately be governed by underlying code. But even the most sophisticated programs have limits. When processing power is stretched too thin, say, when simulating the extreme densities of the early universe, the system might simplify calculations by collapsing complex interactions into singularities. These shortcuts could manifest as primordial black holes, cosmic placeholders where the simulation offloads computations it can't render in full detail. It's not so different from how video games reduce distant objects to low-resolution models to save memory, except here, the objects are regions of spacetime where gravity becomes too intense for even the simulators to handle. This idea isn't entirely science fiction. Some theorists argue that if our universe is a simulation, we might find evidence in the form of mathematical irregularities, tiny deviations from the laws of physics that hint at underlying computational rules. Primordial black holes could be prime candidates for such anomalies. Their formation wouldn't require the usual stellar collapse, making them harder to explain through conventional astrophysics. If PBHs cluster in patterns that defy randomness, or if their masses follow a distribution that mirrors computational optimization like specific power law scales, it could suggest something deeper at play. Imagine discovering that every PBH in the universe weighs exactly 1 trillion tons, not because of natural processes, but because that mass represents the most efficient data compression for the simulation. But here's where things get really speculative. If PBHs are simulation artifacts, their behavior might reveal the rules of the underlying code. For instance, Hawking radiation, the slow leakage of energy from black holes, could be the simulation's way of cleaning up unused data like a cosmic garbage collector. The holographic principle, which suggests black holes store information on their surfaces, might align eerily well with how data is encoded in certain types of error-correcting codes. Even the bizarre entanglement of particles near a black hole's event horizon could mirror how information is linked in quantum computing. Of course, this theory stretches the limits of testability. How could we ever distinguish a glitch from natural phenomena? One approach involves searching for patterns that shouldn't exist, like PBHs arranged in perfect geometric shapes, or their mergers producing gravitational waves with unnatural harmonics. Another wild idea proposes that if the simulation has a pixel size, a smallest unit of spacetime interactions with PBHs might reveal it, like how a digital image breaks down into visible squares when zoomed too far. Philosophically, this forces us to confront uncomfortable questions. If PBHs are evidence of a simulation, does that make them flaws in the system or intentional design choices? Are we, as conscious observers, meant to notice them, or are they the cosmic equivalent of background processes, invisible to all but the most determined investigators? And if the universe is simulated, what does that say about the nature of reality itself? For now, the simulation hypothesis remains more thought experiment than testable theory. But the mere possibility ties primordial black holes to one of humanity's oldest debates. What's real, and how would we know? Whether they're natural phenomena or digital artifacts, PBHs challenge us to look deeper, not just into space, but into the very foundations of existence. And if we ever do find proof that they're more than they seem, it wouldn't just rewrite astrophysics. It would redefine everything. Deep in the void between galaxies, particles scream through space at energies so extreme they defy everything we know about physics. These are ultra-high-energy cosmic rays, subatomic projectiles packing as much punch as a professional fastball, all concentrated into a single proton. For decades, astronomers have traced their origins to violent cosmic engines like supernova remnants or active galactic nuclei. But what if some of these particles owe their absurd speeds to something far older and darker? Enter primordial black holes, the universe's original particle accelerators, lurking in the shadows and hurling matter across the cosmos with gravitational fury. Unlike their stellar-born cousins, PBHs don't need swirling accretion disks or collapsing stars to rev particles to relativistic speeds. Their secret lies in their pristine, uncluttered environments. Picture a lone primordial black hole drifting through a sparse cloud of interstellar hydrogen. As atoms wander too close, they're ripped apart by tidal forces, their electrons stripped away, and their nuclei whipped into a frenzy. But here's where things get wild. The black hole's event horizon isn't a perfect sphere. It's a maelstrom of frame-dragging spacetime, spinning like a cosmic tornado. Charged particles caught in this whirlpool experience forces akin to surfing an infinite gravitational wave, gaining energy with each orbit until they're catapulted outward like bullets from a railgun. These PBH-powered particles wouldn't just be fast, they'd be anomalously fast. Traditional cosmic ray accelerators, like supernova shockwaves, have clear energy limits dictated by the size and lifespan of their stellar engines. But a primordial black hole's acceleration mechanism operates on pure spacetime geometry, potentially pushing particles beyond those ceilings. Some models suggest PBHs could produce cosmic rays with energies exceeding 10 to the 20th electron volts, so powerful they make the Large Hadron Collider look like a children's toy. When observatories like the Pierre-Auger array detect these ultra-high-energy outliers, they might actually be catching glimpses of ancient black holes flexing their gravitational muscles. But the real smoking gun could lie in the particles' paths. Cosmic rays from conventional sources often arrive tangled with the magnetic fields of galaxies, their origins obscured by eons of interstellar wanderings. Particles flung by PBHs, however, might carry telltale signatures, unique energy distributions or arrival directions clustering near regions where dark matter and presumably PBHs congregate. Imagine mapping the sky and finding cosmic ray hotspots aligned with gravitational lensing anomalies or unexplained microlensing events. That kind of correlation wouldn't just hint at PBHs, it'd scream their presence from the rooftops of the cosmos. Of course, PBHs aren't the only suspects in the cosmic ray mystery. Active supermassive black holes, gamma-ray bursts, and even decaying super-heavy dark matter particles could all contribute to the particle pelting our atmosphere. The challenge: untangling the fingerprints. While PBH-accelerated rays might lack the gamma-ray afterglows of blazars or the neutrino counterparts of collapsing stars, they could dominate the highest energy regime. The "oh my god" particles that leave physicists scratching their heads. Future detectors like the planned Cherenkov telescope array might finally spot the subtle patterns that distinguish PBH contributions from the cosmic background noise. What's truly mind-bending is the scale of this idea. A primordial black hole the size of a grapefruit could be silently flinging protons across galactic distances, their impacts echoing in detectors built to study particles smaller than atoms. These unseen relics wouldn't just be passive fossils, they'd be active participants in the universe's particle ecology, shaping the high-energy landscape in ways we're only beginning to understand. And if we're right, the next time a cosmic ray shatters Earth's atmosphere, it might carry not just energy, but a message from the universe's darkest, oldest accelerators. The universe's death may not come with a bang or a whimper, but with the slow, silent evaporation of the last primordial black holes. In the unimaginable expanse of the far future, long after stars have burned out and galaxies have faded to darkness, these ancient relics could be the final actors on the cosmic stage. As they radiate away their remaining mass through Hawking radiation, their demise might mark the true end of the universe as we know it, or perhaps the quiet beginning of something entirely new. Picture a cosmos so old that protons themselves have decayed, dismantling all matter into a thin haze of subatomic particles. The temperature of space hovers just above absolute zero, and time stretches into meaninglessness. Yet somewhere in that infinite void, a lone primordial black hole smaller than an atom but heavier than a mountain finally reaches the end of its trillion-year lifespan. In a flash of gamma rays, it vanishes, leaving behind only a whisper of radiation. That moment could be the universe's last flicker of structure, the final instance where gravity and quantum mechanics lock in their cosmic duel before fading into equilibrium. But what if death isn't the end? Some theories suggest that the extreme conditions of a PBH's evaporation could birth something astonishing, a new universe. In loop quantum cosmology, the singularity inside a black hole might not be a dead end but a bridge to another spacetime. As the last primordial black holes dissolve, their final instance could create quantum fluctuations so violent they trigger a new Big Bang in a separate pocket of reality. It's a fractal vision of existence, one universe's death becoming another's birth, with PBHs as the seeds of an infinite cycle. This idea isn't pure speculation. The math of bouncing cosmologies shows that under certain conditions, the collapse of a black hole could rebound into expansion, like a spring compressed to its limit. If primordial black holes contain even minuscule traces of exotic matter or negative energy leftovers from the universe's birth, they might warp spacetime in ways that open doorways to new cosmic epochs. Think of it like a cosmic Russian nesting doll. Our universe might sit inside the evaporation of a PBH from a prior cosmos, while its own black holes gestate universes yet to come. The implications are staggering. If true, the primordial black holes drifting unseen today could be cosmic time capsules, destined to outlive stars, galaxies, and even entropy itself, only to become the architects of realities beyond our imagination. Their quiet persistence might weave an unbroken thread through the life and death of existence, connecting the first moments of creation to the birth of whatever comes next. And if we're fortunate enough to uncover their secrets, we might glimpse not just the fate of our universe, but the infinite tapestry of which it's just one thread. From dark matter architects to cosmic-scale quantum computers, from multiverse shrapnel to potential time capsules of lost physics, primordial black holes aren't just objects. They're portals rewriting the rules of reality itself. we've journeyed through 30 theories that stretch from the birth of the universe to its farthest future, each one revealing how these ancient enigmas force us to rethink everything we know. Could they be the invisible glue holding galaxies together? The hidden seeds of supermassive giants, or even artifacts of universes beyond our own. The sheer breadth of ideas, from Hawking's evaporating remnants to holographic data vaults, from neutrino-forged anomalies to simulated glitches, proves one thing. When it comes to PBHs, the universe is stranger, wilder, and more interconnected than we ever imagined. What's astonishing isn't just the diversity of theories, it's how they collide. A single primordial black hole could simultaneously be a dark matter candidate, a gravitational wave source, and a relic of cosmic inflation. Their existence ties together quantum mechanics and general relativity, particle physics and cosmology, the infinitesimally small and the astronomically vast. They're the ultimate cosmic crossroads where unanswered questions meet daring solutions. Whether they're lurking in our solar system, powering unexplained gamma-ray bursts, or encoding secrets of extra dimensions, PBHs don't just fill gaps in our knowledge, they tear those gaps wide open, revealing how much we've yet to learn. This isn't just theoretical noodling. Every year, new observations, gravitational waves, microlensing events, anomalies in the cosmic microwave background bring us closer to confirming or refuting these ideas. The next decade could deliver definitive proof that PBHs are out there, hiding in the darkness, or it might force us down even stranger paths toward theories we haven't yet dreamed up. That's the thrill of science. The universe always has another card to play, another mystery to unfold. So now it's your turn. Which of these 30 theories blew your mind the most? Are you team PBHs as dark matter, or do you lean toward the multiverse collision idea? Maybe you've got a wild theory of your own. Drop it in the comments and let's geek out together. If you're hungry for more deep dives into the cosmos' biggest mysteries, smash that subscribe button. We've got black holes to unravel, quantum enigmas to decode, and a universe full of wonders waiting to be explored. Until next time, keep looking up and remember, the darkest corners of space might just hold the brightest sparks